Good day, everyone. We are Group 4 and we are going to report about the membrane action potential experiment with the squid neuron. Before anything else, let's define what the membrane potential is. Essentially, it is the difference in voltage or electrical potential between the opposite sides of the cell membrane due to the unequal concentration and permeability of ions across the semi-permeable membrane. The difference in the concentration of ions lies on the fact that positive sodium ions have high concentrations outside the cell, since the cell membrane is highly impermeable to them. On the other hand, it is highly permeable to potassium ions that leak through the leak channels. Because of the concentration of sodium ions outside is greater than that of the potassium inside, the cells have negative intracellular potential. This negative potential causes the electrical forces to direct the positively charged ions such as potassium, sodium, and calcium into the cell. At the same time, concentration forces direct the inward flow of sodium, calcium, and chloride ions and an outward flow of potassium ions. To balance the inward and outward flow of ions, sodium-potassium pumps, ion transporters, leak channels, and voltage-gated channels exist on the cell membrane's surface to regulate the entry and exit of the ions. This regulation gives way for sudden influx or efflux of the ions, which gives rise to what is observed as a characteristic spike, or the so-called action potential. The action potential requires a certain amount or threshold of current, which then causes the sodium channels to open, which leads to a rush of sodium ions inside, depolarizing the membrane. After a while, the potassium channels will then open and cause a repolarizing event and the subsequent hyperpolarization due to it staying open longer than that of the sodium channels, before it goes back to its resting potential. Action potentials function as electrical signals for cellular signaling and communication for processes that involve the system such as the nervous system as well as the muscular system. The objectives of the experiment were to perform the Labster virtual laboratory simulation involving membrane action potential and determine the unknown toxin, to explain the concept and importance of membrane potentials and equilibria in biological processes and the different techniques used, and to determine the effect of different ion channel blockers on the action potential.
To obtain the aforementioned objectives, the following procedures were performed. But before that, in principle, action potentials are stimulated in the dendrites of a neuron after a neurotransmitter triggered the influx of positive ions through the neuron membrane. Action potentials are then propagated along the length of the axon to the terminal buttons where they will in turn stimulate the release of neurotransmitters to transfer information to the next neuron through the synapse. Dr. Alan Hodgkin and Dr. Andrew Huxley in the middle of the 20th century proposed a modern model for the propagation of an action potential down the axon of a squid neuron. Squid axons are used because they are unusually large, allowing researchers to see cell components move and material within the axon can be manipulated, while the processes involved in transport are still intact and operating. Vital tools to observe action potentials include a micropipette that contains a conductive wire which will transfer the desired current. To make a microelectrode that can be inserted inside the squid's giant axon, the glass pipette was stretched to the desired thinness first, which was 0.1 mm in diameter. Using a micropipette puller, a large glass pipette was pulled until the glass became so thin it broke in two. A chloride-coated silver wire was inserted in the glass micropipette made to obtain a microelectrode which looks like the one shown in the figure. These electrodes serve an important role in recording membrane potentials, which are the difference in electrical potential between both sides of the membrane due to the different concentrations of charged ions. The microelectrode was then inserted into the giant axon by carefully making an incision in the side of one end of the axon with a scalpel. At last, the axon was ready to be used after it was set up in the test chamber.
We begin by discussing the equilibrium membrane potential of the squid axon. These are the measured concentrations of different ions, namely sodium, potassium, and chloride ions in the lumen and outside of the squid axon. Using the Nernst equation, we can calculate the membrane equilibrium potential for a specific ion in a stable situation where no substantial flow of ions is taking place. As shown on the Nernst equation on the right side, the equilibrium potential depends on the temperature T, the universal gas constant R, the Faraday constant F, the charge of the ion Z, and the external and internal concentrations of the ions. Substituting the corresponding values in this sample calculation for the equilibrium membrane potential for sodium ion, we calculate a potential of positive 55 millivolts for sodium. In a similar manner, we calculated the potential for potassium and chloride ions and obtained the following values: negative 75.6 millivolts for potassium and negative 59.9 millivolts for chloride ions. Each of these ion concentration and resulting equilibrium potential contribute to the overall resting membrane potential. In the case of a squid, it is around negative 65 millivolts, while for humans, it is around negative 70 millivolts. To further explain this resting membrane potential, we show this illustration of the membrane along with the measured ion concentrations. The concentration gradients of each ion causes the sodium and chloride ions to move inside the neuron if there is a path for this to occur, and will cause potassium ions to move out of the cell. As a result, the entry of positively charged sodium ions into the lumen will depolarize the membrane, making it more positive. In contrast, the potassium ions leaving out of the lumen of the axon will take their positive charges with them, thus hyperpolarizing the membrane or making the inside of the cell more negative. Likewise, the movement of negatively charged chloride ions inside the cell will further polarize the membrane and the negative potential will drop. To test our understanding, there was a question in the activity quiz which asked us to predict the resting membrane potential of a particular cell if this cell is equally permeable to chloride and potassium ions. The given equilibrium potential for chloride is negative 60 millivolts, while for potassium is negative 90 millivolts. To solve this problem, we use the Ohm's law. First, we define that both chloride and potassium currents have equal magnitudes but opposite directions. Incorporating this to Ohm's law, we equate the two expressions and substitute the corresponding values, which finally leads us to the calculated resting membrane potential of negative 75 millivolts. Since that's clear now, let's go back to our virtual lab experiment. Now, to study variations of electrical current, clamping techniques are employed. In the virtual simulation, two techniques were conducted, which are the current clamp and the voltage clamp techniques. In the current clamp technique, the current will be set at a specific amperes and the resulting voltage will be recorded. In contrast, the voltage clamp works by setting the voltage at the chosen value and the resulting variation in the current is recorded. As such, these two techniques are complementary with one another. The results of the current clamp technique lead to the generation of a standard action potential graph as shown. The shape of the graph shows three phases. First, the depolarization phase, wherein the membrane potential changes from a negative resting potential into a positive value. This is followed by the repolarization phase, where the membrane potential returns to a negative value. And finally, there is a short hyperpolarization phase wherein the membrane potential drops below the resting potential. And after this, the membrane potential will go back to its resting potential. The mechanism behind these steps will be further explained later by Lei. For now, we will first discuss the identified ion transfers responsible for each phase. Let's begin with the depolarization step. Looking at our current ion concentrations, it is most likely that the entry of positive sodium ions is responsible for depolarization. With that, we tested the activation of voltage-gated sodium ion channel using a voltage clamp technique at different voltages. The resulting current time and voltage time graphs are shown. As can be observed, there is no changes in the current with the membrane clamped at negative 80 or negative 60 millivolts, but all of the other subsequent voltages have varying current events. This no change is attributed to these two signals being below the threshold to open ion channels to trigger depolarization. Meanwhile, voltages greater than 55 millivolts, which is what we calculated as the equilibrium potential for sodium using the Nernst equation earlier, causes the direction of the current to reverse, and sodium ions will move out of the axon. Now, to test the specificity of the sodium ions for the depolarization step, we also repeated the voltage clamp experiment using calcium 2+ ions this time. As shown in the resulting current time graph, calcium ions seem to not trigger any depolarization at any voltage regarding action potentials.
Seen on the standard action potential graph, in repolarization, the membrane potential returns to negative voltage values. Since the membrane potential is with respect to the intracellular environment, this means that repolarization would be triggered either by 1. Flow of negatively charged ions like chloride into the axon, or 2. The outward flow of positively charged ions like potassium to the extracellular matrix. In the simulation, the respective effects of chloride and potassium ions on repolarization were investigated. If the movement of ions is from high concentration to low concentration, hypothetically lowering the external chloride ion concentration to 0 would drive the ions inside the axon to flow out, making the membrane potential more positive. Therefore, repolarization is blocked. To put it simply, if there are no external chloride ions to move into the axon lumen, there would be no repolarization. To determine whether chloride ions play a role in repolarization, the effects of different concentrations of external chloride ions on an action potential were tested, and the graph on the right is generated. Seemingly, it doesn't show significant differences from the standard action potential graph. This would mean that the inward flow of chloride ions is not the main factor responsible for repolarizing the membrane. Since the inward flow of the chloride ions is not the main driver for polarization, this calls for probing the role of potassium ions in the said process. Hypothetically, raising the external potassium ion concentration to 400 millimolars would prevent the flow of potassium ions from leaving the axon. This will be more apparent when the effects of different potassium ion concentrations and action potential will be tested, to be shown in the next slide. From this graph, it can be gleaned that lower external potassium ion concentrations lead to quicker repolarization, whereas higher external ion concentrations prevent repolarization from happening at all, as mentioned a while ago. This confirms that the outward flow of potassium ions play a role in repolarization and hyperpolarization, which will be subsequently discussed. As a recap, we will be looking into the action potential steps in the Squid axon. At the initial state, the sodium and potassium ion channels are still closed. Notably, there is a higher external sodium ion concentration and lower external potassium ion concentration, all relative to the inside of the axon. Moreover, the resting membrane potential is negative 65 millivolts. The high voltage of the upcoming action potential will trigger the opening of voltage-gated sodium ion channels. The sodium ions will flow into the lumen of the axon due to the concentration gradients, triggering the depolarization and the increase of membrane potential to positive 40 millivolts, through which the sodium ion channels will be temporarily inactivated, thus preventing another action potential to trigger too early after the other. Potassium ion channels will also open, but to note, the activation kinetics of potassium ion channels are slower than that of the sodium ion channels. Consequently, the potassium ions will exit the cytoplasm of the axon, triggering the repolarization. Sodium ion channels will then close while the potassium ion channels are still open. This would lead to hyperpolarization. This phase is seen as a slight dip following the spike.
A period of increased potassium permeability results in excessive potassium efflux before the potassium channels close. The potassium ion channels will close, and the sodium-potassium pump will swamp the ions across the membrane to return it to the initial resting state.
Ion channel modulators are molecules or drugs that affect the activity of the ion channels by either blocking or opening them. They could be cations, anions, or specialized biological molecules like neurotoxins. Neurotoxins act as a blocking agent that prevents the ion channels from functioning and propagating information properly. But other modulators have long been used in therapy due to their highly specific nature, which can target and treat the channels that contribute to diseases such as neurodegenerative ones. There are also other diseases that are treated by the modulators that target these specific ion channels. The calcium ion channel blockers have shown the therapeutic effect against hypertension, while potassium ion channel blockers have shown effect for heart arrhythmia. Sodium ion channel blockers, on the other hand, have two types. The extracellular ones are usually toxins, but the intracellular ones can be used in anesthetic and anticonvulsion. Chloride ion channel blockers have been less studied but are showing potential in treating secretory diarrheas and kidney stones. In the experiment, 3 compounds with known effects to the membrane potential were compared to the unknown compound to determine its identity. Current clamp mode was employed and the changes in the action potentials were observed over an increasing concentration of the compounds. For compound A, a decreasing trend was observed in the membrane voltage. This could be due to compound A inhibiting the polarization of the membrane by blocking the voltage-gated sodium ion channels. Thus, we can say that the compound A is a voltage-gated sodium ion channel inhibitor. Next, compound B exhibited a loss of the hyperpolarization phase and subsequent blocking of repolarization. This could be due to compound B targeting the potassium ion channels and inhibiting the repolarization and the maintenance of the resting membrane potential at high concentrations. As such, we can say that compound B is a potassium ion channel inhibitor. As for compound C, the membrane potential nearly plateaued and stayed depolarized. This could be due to compound C inhibiting the inactivation of sodium ion channels, thus there would be a continuous flow of positive charge. Therefore, compound C is also a voltage-gated sodium ion channel inhibitor. To determine the identity of the unknown compound, it was also subjected to the clamp, which resulted in a graph similar to that of compound A's. Thus, we conclude that the unknown compound is also a toxin that causes a blockage in the depolarization of the membrane, which in turn is due to the targeting of the sodium ion channels. The unknown toxin's identity may be tetrodotoxin, which selectively targets and blocks the voltage-gated sodium channels of the nerve cells by binding to the neurotoxin receptor 1 site of the alpha subunit of the sodium ion channel. According to CDC, tetrodotoxin may be acquired by ingestion of certain species of fish, shellfish, octopus, and amphibians, and that it triggers partial to total muscle paralysis, which may be fatal in some cases.
There are also other clamping techniques which can be used to accurately measure cell potential. These techniques are advantageous in various laboratory and industrial applications. For instance, the patch clamp technique allows the investigation of a small set or even single ion channels. The membrane potential of the cell is measured and compared to the command potential or the reference potential. If there are differences between the command potential and the measurement, a current will be injected. This compensation current will be recorded, allowing conclusions about the membrane conductance. The membrane potential can be manipulated independently of ionic currents, and this allows investigation of the current voltage relationships of membrane channels. This technique makes use of a hollow glass tube filled with an electrolyte solution in which there is a pair of electrodes connected to an amplifier. The first electrode is put into contact with the membrane of a cell, and another electrode is placed in a solution around the cell. The circuit forms between the recording and reference electrode. Application of the patch clamp technique can demonstrate the existence of ion channels and provide valuable information for ion channels, including their electrophysiological properties, molecular structures, and the mechanism of drug action. Through clamping techniques with some of the examples discussed, membrane selectivity and permeability towards ions are determined, which helps in the physiological understanding of cellular processes. By these techniques, structure-function relationships of ion channels were elucidated that not only support the homology already suggested by amino acid alignments of different channel types, but that also pointed to regions important for gating, ion selectivity, or subunit interaction. Currently, effort is being made to develop automation of the technique, which will result in a cost-effective, fast, and highly accurate method to test for drug actions on high-throughput scales.
In conclusion, the Nernst potential describes the electric force that balances the chemical force so that there is no net ion movement. The shape of a standard action potential graph shows three phases, namely the polarization, which is influenced by the inward flow of sodium ions to the axon, the polarization and hyperpolarization, which are linked with the outward flow of potassium ions to the extracellular matrix. Lastly, the unknown neurotoxin in the simulation was determined to be tetrodotoxin, which is a voltage-gated Na+ channel inhibitor. For the recommendation, it is recommended to test and identify various neurotoxins, their modes of action, and respective effects on nerves. Thank you for listening. If you have any question, feel free to comment them down on the discussion board and we'll get back to you.